Hello to viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about Lightmatter, Photonic, Superchip. So let's dive deep into it. So what exactly is the problem that we need Lightmatter, Superchip? Well, problem is that our compute requirement is growing exponentially, meaning if you actually take a 90s desktop, your remote control most likely has more horsepower than that. So like the demand, like the amount of crunching we want to do is stupendously high. And AI, this new thing that happened in the last 5 years, it requires massive cluster, not only compute, but cluster, because there is a fundamental fact that you have to understand. While silicon has made amazing progress, like the amount of cut you can do, it's ginormously awesome at this point. And like this is so good that we cannot measure it, like, even in decibel. We have to measure it in freaking log. Like it's not 10 to the power 10, 10 to the power 100, 10 to the power 10,000. Like it's stupid. Like the amount of you can do on silicon, it's bonkers. However, let that be clear, no matter how much power one silicon can do, two will be able to do more. And you can't make one silicon very huge simply because where would you get the stock material? The silicon disk that we now manufacture, they have a physical diameter limitation, so you can't do much. And you may not want to make super huge silicon because it does make the ability to pump power and ability to deal with errors and all that kind of difficult. Like there is a what you call sweet spot. You can make silicon big, but you do not want to be huge. So there is a sweet spot. And again, even if you can make it like, wafer size, as they call it, wafer size silicon, it's still wafer size. You cannot make a wafer that is kilometer long. So fundamentally, while the progress on the silicon itself is magnificent, you will reach a point where it's like, yeah, we might be able to do more if we can stack multiple of that. That's the whole point of cluster. If single unit can't crunch through it, let's just add 10,000 of those or 50,000 of those. And no matter how powerful your node is, it can't compete with 50,000 more nodes. So that's the whole point. However, compute cluster fundamentally means you have the ability to communicate between one CPU to another CPU that could be on the other side of the, basically, your building. Like if it's next to it, basically the latency, the throughput, all of those things have to be basically low penalty enough where it's like, bro, it does not matter. The data should be able to run like, yo, I have this many nodes. It should not be like, oh, this is closed node, like how we have in CPU, what we call L1, L2, L3 cache. That should not be there. Ideally, you should be able to, like, bro, it's all one cluster. Now, back in the old days, it was not an issue. We were way too slow. But now we are reaching a point where this graph is making sense, as in compute good, awesome, GG, and interconnect, yeah, it's lagging behind so badly in normal desktop, it actually rolled back. Like if you look into basically when did we got 1 Gbps internet, ethernet port, very long ago, when did we got 10 Gbps? Just few years later. Here's the deal, it went backwards. We went from 1 Gbps to 10 Gbps to, yeah, nobody is buying it, let's go back to 2.5 Gbps. At this point in time, 2.5 Gbps is there, 5 Gbps is there. It's like, yeah, like we rolled back. Like your USB went twing, your Ethernet went swing, come back. It's too fast. So realistic, and be mindful, that same thing applies on ginormous data center also. And again, that's why NVIDIA bought Mellanox, simply because they're like, yeah, we can't make AI servers if we do not have good control over the switches that are connecting these things. If weak switches, outcome weak output. So they needed quality control. They're like, hey, let's just buy the goddamn company. So they bought it. So NVIDIA got that leg up. That's why they can make such a good delivery on basically your AI cluster, simply because they control the whole thing in single house. But again, inherently there's a physical limit. Interconnect has not been growing, and your SoC has reached a point where it's like, bro, we can do so much more. It's just that latency is so high. And again, latency is on physics level. You can't bypass it. You can't like, okay, I'm gonna code it. Nah, it takes time for data to go from this CPU to CPU that is on the other side of the building. It will be slow. And again, you can reduce it, but you can't eliminate it. So the game becomes how stable and how minuscule that noise can be, like how insignificant you can make it to be. So interconnect is falling behind the system on chip market, so to say. Basically, this puppy is the ugly part, this is the GG part, but both of them have to be married. So that's the fundamental problem. You can see, like, it's a huge gap. So what's the core technology? Now, there has been massive development in fiber optics. We kind of realized that electrically you can't really send too much data long enough. As in, like, you can have a CPU to PCI Express, but even that starts to reach into interference issue. So we learned it the hard way that you can't actually connect from one to another without going fiber. So, okay, we went into fiber. So fiber has been growing exponentially. And again, the biggest jump in fiber, that turbocharged fiber, was what we call Ethereum doped fiber amplifier. The idea was long ago is that you had undersea fiber cable. So you sent the electrical signal, photonic signals, that was the actual data. It went, let's say, 100 kilometers. Then there was a receiver. Receiver took it, converted into electrical signal. Now emitted that with a lot of power. Yes, there had to, in that undersea fiber, there was a lot of actual electrical wiring also, just so they can power, like, middle of nowhere, that amplifier. But again, that itself was a problem because you are converting from photons to electricity, then re-emitting. That was adding latency. Some super awesome scientist figured out, hey, what if we have a fiber that is almost ready to burst and then you send a weak signal through it? It will get amplified at light speed, meaning there is no conversion, there is no extra latency. So that allowed fiber optics to become the system, like GG, because again, you can amplify signal at light speed. So lot of development happened in fiber. And then we reached a point where it's like, okay, we can't switch fiber on and off very quickly, simply because even though you could roughly make an electronic that is fast enough to drive a LED element, aka your diode, laser diode does not lace that quickly. As in, like, it takes a sweet time. It's like, okay, there is a curve to it. So they're like, yeah, that's not gonna work. So they had to create a system where it's like laser is on, the end. Laser is always on, like you're sending laser at full power, and then you have some element that is doing on and off, not the laser. Laser is fixed power output, what we call continuous wave. So how did we do that? Like, you have a laser light, of course you can't have a mechanical shutter going off on and off. How do you do that? Well, we started a Mach Zehnder modulator, MZM, and it was surprisingly magical. It's like they have it and they phase shift it. It's like they just twist photons. I'm like, damn. Then it was big, it worked, but it was like, okay, not very small. Like, it worked, but not very small. Then somebody came up with the idea of electro-absorption modulators. So basically, you almost have a structure and you're sending photons through it, and you can change its refractive index. Like, literally, you can make the material transparent or translucent or opaque based on the electrical field strength, so to say. So that was electro-absorption modulator. GG. And then somebody smoked something good. Then they got into micro ring modulator. Now, this is black magic technology. I have no idea how the heck humans are smart enough to make this, but they do, and it works somehow. MRM, this is the current technology. Yeah, this puppy can leach energy from fiber, so to say. So assume you have a fiber, right? Assume the fiber have lot of wavelength, and be mindful, when we are talking about wavelength, we are not talking the wavelength as you think, like, red, blue, green. Even though they use that to showcase it, the wavelength is very tight, because again, fiber is transparent to only one wavelength, or like that band, so to say. So this would be like 1470 nanometers to 1610 nanometer. It won't be like, okay, 1470 to 400 nanometer. You can send fiber with that many channels, but it will be very inefficient. Fiber will heat up and might even burn up. So we generally have to compact it within the transparency band. Basically, depending on the fiber you are buying, it will have like I think C band and O band. So based on that, you will have, like, one channel would be on 1470, another channel would be 1490, another channel would be 1510, 1530, 1550. Basically, how we used to do it in old FM radio in car. That's how you have that. Okay, cool, awesome, GG. But here's the deal. This black magic technology, it has the ability to leach it. Meaning, imagine sending this signal through an optical fiber. Okay, you're sending it. This puppy can select it. It's like, bro, come here. It can just go inside the fiber without physically touching it. It's just like, come. Fiber is going. It's like, basically, you can send 10 channels to it. One channel can disappear, and nothing else will happen. Like, nothing else. None of the channel will have any interference, any polarization, nothing. It's just like, come here. It's like, whoosh. So how do we mathematically describe it? We call it Q factor, quality factor. This puppy starts at 10,000. 10,000 is the lowest quality factor here. What does that mean? That simply means how precise you can do. Now, we used to do CWDM. Basically, each channel was around 20 nanometers apart. Okay, so 20 nanometers apart, not that far apart. And then like, okay, we got like Q factor of 10,000. Someone's like, okay, now we do DWDM, dense wave division multiplexing. Now what is the gap? 0.8 nanometers. Let that sink in. The tuning knob that you have has to differentiate between 1 nanometer and 1.01 nanometers. Like the gap is tiny. Like here it was like, oh, 1470, 1490. Here it is 1553.33, 1552.52, 1549.32. Like it's tiny. It's not even one whole nanometer. And this puppy, because the Q factor is so high, and be mindful, 10,000 is the starting point. There are some engineers who are working on it. It's like, bro, that's nothing. We are working on million. I'm not even joking. So they can just have the fiber signal going, and it's like, oh, that's my wavelength. They just take it out. Oh, by the way, it works both way. Meaningly, if you have a basically continuous wave laser, it is sending signal. How do you modulate it? Ring laser will have the ability to leach energy, dump it into a medium, or let it go through. So let it go through means full signal. So that is 1 and you're like, okay, I want to reduce it to, let's say, 75% or 33%. You drop it by 33, that becomes 10 signal. They're like, okay, let's drop it another. Then it becomes 66 at that point it's 0 1, and then you're like, okay, completely broke it, that's 0. That's what we call PAM4 modulation. That's how it works. Basically, you have a laser that is sending out all these things, and you are leeching one of them, on off, on off, on off, on off. And again, it's not just on and off. You are like level 1, level 2, level 3, level 4. You have 4 level, PAM 4 level. That is doable nowadays. And same works in the reverse also. So same rings, the physical rings are basically leaching energy, and they are dumping that energy into receiver aka photodiode. Photodiode is converting your photons into electrical signal. That's how your computer is reading it. And again, it works in reverse with basically CMOS driver. You heat it up to change its systems or like voltage. Generally, I've seen a heater used, and again, they are sending currents to it to heat it up. So it blocks 75%, block 50%, block 25%. That's how it works. So, continuous wave laser is the source, and then you just slice it up. And why do we go through like, on and off to like this 4 levels? Well, somebody figured out that you can increase the signal frequency, right? You can go from 10 hertz to 20 megahertz to 50 megahertz. You will reach a point where it's too finicky. And again, you can easily notice that PCI Express 3.0 to 4.0, engineers hated that. 4.0 to 5 jump is like, ooh, and 5 to 6 is like, yeah, we are not even touching that. Motherboards would be stupendously expensive simply because the signal routing, it becomes a very finicky. Because again, once you keep increasing the frequency, everything else matters. Like it's so much like at super high frequencies, like, yeah, one pulse came back. Every joint has to matter. We reached a point where it's like, yeah, this is stupid. We can't do that. But again, why only have 0 or 1? Right? Why only have that, like in physical domain, why only have like, imagine you have a voltage circuit that goes from 0 voltage to 1 volt. Okay, cool, awesome. But why only go from 0 or only to 1? Like you can, how about 0.1, 0.2, 0.3? Now you have 10 options. And again, you can encode data, digital data into those layers as long as those are clear enough. Now again, in principle, you can have as many level as you can do. It's just that electronically, we have agreed that let's try with 4. So you have fully off, that is 0 0, bit on, that is 0 1, bit more on, that is 1 0, and full on, that is 1 1. So every pulse now carries double data rate. So this is how we are sending a lot more data. Because again, you may be like, okay, why not just increase the frequency? It becomes too, what you call, frustrating. Basically, your chip cost, your circuit cost goes from $1 million to billions of dollars, and nobody's going to buy that. So yeah. So we are doing PAM4. And let that be very clear. As the Q factors will become better, we may be able to add more channels. So these are the few options. Add more channels, add more levels. So PAM4 is just one. PAM8 can be done mathematically. And again, as long as you have clear distinction, you should be able to send the data and retrieve it. So I can easily see in the future, somebody is like, oh, PAM4, how ancient. We have PAMs 128, 128 levels. And again, physics is not stopping you. It's just that, is your engineering good enough? So that's how we do the core development. And if you want to have a job in the future and be like, nobody can touch it, master this black magic technology, micro ring modulator. There are few people on the planet that can do this, only few. And I mean few, as in like collect all the universities, only few of them will be like, yeah, I can handle this. It's a black magic. It's like, we just leech photons. Okay, so far that's a common technology used in very advanced systems, including NVIDIA's. So how this company is different? This company figured out geometry, as in 3D. So the idea is, all right now, you look into any system, be it Broadcom, be it Mellanox, generally they have a chip. Chip does the like actual computation, as in like which data packet has to go where. Cool, awesome, GG. But here's the, how does it communicate through the outside world, as in the photonics world? Well, it goes to the shoreline, as in the edges of the CPU, and that's where it has the fiber optics. And you can understand that this creates an issue what we call parameter to area ratio. You can make a bigger die, but the shoreline, as in the edge, will not grow exponentially, while your surface area will grow exponentially. So that creates, now this is not an issue for GPU, because again, GPU is supposed to ingest data and crunch it. So area is awesome for them. They want to be huge. They want to do more crunching. But you cannot follow the same principle for networking devices, because networking has to go in and out, in and out. How do you do in and out? From the shorelines. That creates an issue. And again, you can see that in NVIDIA's hardware, where they have tiny basically co-packaged modules on the shoreline. That's the limitation. You can't pack so many of it. And if you were like, okay, what if I make the chip bigger? Cool, awesome. And it will increase it, but the area to edge ratio will always be wasteful. So that's a physics problem, what we call parameter to area ratio. You cannot bypass it, you cannot cheat it. It's in the law of the nature. So somebody came up with the idea, hey, why not just go from the bottom, just drill through that puppy. So, and if you understand fiber optics, you understand you can't just drill through it. It's a very finicky puppy, especially working at these sort of speeds. So they're like, hey, they made this layer, which they call passage layer. Now this layer is almost like a PCB for fiber optics. So it can take the fiber and directly dump it into this compute node at the node itself. Like the actual fiber optic equipment, the fiber pathway and the silicon chip, they are in one Z axis. They're literally on top of each other. This is what this company figured out. They can stack those puppies like there is no tomorrow. And now they can be like, hey, we have chiplet design. Meaning, if you're like, hey, we just want a small puppy. Cool, awesome, a small chiplet. You're like, hey, we want a server rack. Whereas like, we are handling, let's say 40 blade. It's like, bro, we got you, bit bigger. They're like, no, we want to have all of, and be mindful, the less nodes you have, as in like the less switch you have, the lower the latency. So ideally you want to have one switch dealing with as much data as possible. But this puppy is like, okay, I got this. Scale it up. Scale it up. Now this puppy is like, okay, I'm handling one whole hall room number one of like, there you can have 100 racks. It's like, I got this. I got this. Me good. 3-dimensional good. Me good. So chiplet technology allows them to scale it up, which again, be mindful, nobody else was like, is that even possible that you can have like fiber directly going from the bottom to the chiplet and getting all the processing and then coming backwards? Is that allowed? And they're like, yeah, we can do it. So at this point in time, there's products. The early products are 400 terabits per second, and they can go higher. Rather, the design and the philosophy, it's a paradigm shift. It's like, oh, we can do this. We can do more of this. So 3D stacking, surprisingly clever use. And again, I have to meet that engineer who figured out this basically passage design. It's like, how the heck you have a structure? And be mindful, electricity is also going back and forth from there. How? How the heck you do not have a polarization change nightmare? How? So what is the scope of this breakthrough, so to say? Well, Lightmatter has a unique solution, which again, be mindful, that was the reason why NVIDIA was buying major networking companies. And again, all other companies are limited by basically networking itself. AMD, even if, let's just assume tomorrow they snap their finger and they have amazing SoC, unless they have a very good partner, let's just say Broadcom, which again, may not be as good as Mellanox, they will not be able to deliver on customer. Customer won't be, whoa. So they need a solution. Like so many companies, like they're like, bro, give us a way of networking thing. Be mindful, you can beat a well-networked device on a crappy, crappily network system. Meaning, if you can exceed performance reasonably well enough, you can have like old GPUs and beat modern one. Simply because latency is on every steps. Latency cannot be bypassed. So they have this unique system, 3D and more, and they can do far more routing in principle than any other. So meaning one U, let's say you have a full blade rack and one U is like, okay, this is how much you get for your routing duties. They're like, bro, we got this. We got this. Like NVIDIA does not got this. We got this. So that's a big deal. And how much data we are talking about? Well, we are talking about 16 wavelength in one fiber. 16 of these puppies. and this is the signal, and let that be clear, that's the PAM4. PAM4 generally does not try to use this level. It's almost like here, you want it to be crisp. You want to be crisp, because again, at base layer there's too much noise, so you want it to be here, and here, and here. So this is what they're doing. They're putting 16 channels on a single goddamn fiber, and that gives you single fiber, let there be a single strand fiber, 800 Gbps. To give you a context, right now if you do that on many servers, they will have like 4 fiber going to your switches. 4 fiber, they're like 1. Right now they can go into old, not old as in like 2025 data centers, is like, yeah, throw away majority of your fiber optics. That's how powerful that is. That is 100 gigabyte per second on one fiber strand. That's good. And they are also working on O-band right now. And again, I have no idea who came up with the name. Apparently, O-band stands for original band, and then you have C-band for conventional band. C-band is used for the deep sea fiber, because again, Ethereum doped fiber only works on those bands, so they're like C-band. So you have O-band, 1260 nanometers to 1360 nanometers. Basically, this 100 nanometer band, they are working on it. Again, okay, company had an idea, company patented it, company showcased the idea. Question is, can they scale it up? Yes, they are saying, again, they are saying that they have dealt with partners and they have these puppies to take care of them. So they have TSMC, they have GF, they have Tower, they have TSMC. And let that be clear, a lot of people have this perception that TSMC is the thing. It is the thing, but it's not the only thing. There are many other companies, including Samsung, including Sony, including other companies also. So having multiple partners, it's a really wise game. You never want to be in a scenario where it's like, China goes boom boom on Taiwan, and then TSMC is like, sorry guys, you do not want that. So you want to have multiple options. So, and there are multiple options. So that is there. They are claiming that they have multiple partners, meaning if some giant corporation pastes some order, like give me 10,000 pieces of this, they're like, bro, we got you. I got you. And what kind of bit rate error we are talking about? On the raw technology itself, they have achieved, again, they are claiming bit error rate of 1.0 E minus 10. Now, what the hell that means? That simply means if you are transmitting 1 gigabyte of data, like 1 gigabyte here to there, the fiber will only throw away 1 bit in 1 gigabyte. Now, like, does that matter? Short answer, no. No, it does not matter. Every networking protocol has multiple layers of redundancy, multiple layers of checksum just to make sure of that. They are designed to handle much noisier data. So if your pipe is really good, checksum becomes what you call redundant. You might be able to reduce the checksum requirement, whereas like, send bigger packets, only checksum for like if you have very crappy signal, you'll be like, okay, checksum every 8 bits. If you're like, it's a good, it's like, okay, check every 16 bit. You do not want to have like too much, because again, if a large data went through and then there was an error, you have to retransmit that large unit. So there's a, give and take. And every fiber engineer, every people who are designing the switches, they have to balance it out. If this technology inherently delivers that kind of good result, they're like, we're good. We can have much larger packet. And again, there will be a time where one error happened, but let's say that error only happens like, in 3 hours. Oh, in 3 hours, you have to resend one packet. That's like, shut up, take money. So that is there. And they are very temperature stable. They put a thermoelectric heater and cooler unit, Peltier module, to basically scale it up from 25 degrees Celsius to 105 degrees Celsius. And this puppy is like, I'm good. And that's the weird part to me, because how the heck diode laser is stable at that point in time? Diode lasers are very temperature sensitive. How the heck they're doing? Is a ring laser sensitive, or they have like some sort of mechanism to compensate for it? That's weird to me. But again, doable. Is just that how. So that is there. And they are also polarization tolerant, because again, at low speed, it does not matter. Once you go stupid speed, it matters a lot. Polarization, as in like if fiber twists, the data twists itself. And again, lightning for some reason creates enough of an EM pulse that it does cause an issue on fiber links, especially at high speed. Low speed is like, who cares? High speed, yeah, ooh. Again, that's just noise. Let that be clear. It will not affect you, because again, error correction rate would be like, I got you, fam. So, and be mindful, is this really as big as they are advertising? To give you a context, how big latency is, Meta, aka Facebook, they had an issue. They were analyzing their hardware resource utilization, and it was full. But again, they were feeling it's not really being utilized. Why? Clock. Every computer has a clock, but here's clocks are drifty. If you are looking into physical hardware, clocks are lol. Like your motherboard clock is lol. If you rely on it, it's a lol. It's gonna lose few seconds. Now, like, okay, what if I have temperature compensated? Bit better, but not that much better. And like, okay, what if you have ovenized diodes that is giving you basically temperature controlled environment, it will not be that good. And be mindful, no motherboard has that. So they're like, okay, what does that mean? That simply means every computer has to wait after receiving a time signal, because again, if you directly process the clock signal, I received the signal, I process it, you could receive a time because if one of the oscillator drifted, which all of them do, it will be like, yeah, this signal came from the future. Computer will like, look bro, my clock is only at this time, this signal is coming either from my back or my future. It will corrupt everything. So people generally give buffer room. And be mindful, this is on time domain. You can't do anything about it. You can't increase your gigahertz, you can't increase your RAM frequency. It's on the time domain. You have to wait. You're like, come on, 1001, 1002. Of course, it's in microseconds, but it is there. So they're like, hey, what if we put atomic clocks in all things? Normal atomic clocks. These are in your mobile phones and all that. Simple atomic clock. But to make sure that it does not drift, they have GPS receiver, as in GPS is the world's time reference. So they take that time reference, lock it to local time reference of atomic clock, and then they are like, okay, now switch every server to nanoseconds and assume all of their clocks are working reliably. They got more boost out of the same hardware. They're like, this hardware is like, the hardware was breathing. Same thing will happen with this. Assume like you have A200 versus A100. A100 with this sort of system, where every latency is shrunk down, it will be like, oh, I can train the AI in 5 months, while A200 will be like 6 months. Simply because of the latency. Latency is happening on time domain. You can't do anything about it. So scope is massive. And be mindful, this is Gen 1 technology. I'm like, dang. Imagine they actually start to manufacture it and they're like, hey, we can do even better. Like, imagine a one ginormous switch, which is like, I am handling 500 servers. Like the latency reduction would be like, shut up, take money. So what can we expect in the future? Well, reality is we reach the maximum possible of current technology. As in, like, I have seen way too many professors saying that, yeah, this sort of silicon, it is reaching a point where it's like, yeah, you can have design improvement, you can have heat improvement, but you're not going to get too much better. And again, you can see that like 8 gigahertz CPU was achieved, AMD Bulldozer achieved it. You still don't have it. That again, thermal limitation. Like there are physics points that's like, yeah, you can't go much. And again, same goes in the signal also. That's why we have switched to non-zero return to basically PAM4. So we have reached kind of what we can do, simply because it takes more energy to compute basically computation on a bit. Like you have 0 bit, convert it into 1, not do anything or delete it, whatever you have to. Those takes much little energy compared to transmitting the goddamn energy. Basically transmitting basically 1 bit data, it will take, let's just say 1 coulomb. It will take 15 coulomb to transmit it from here to there. So that here to there, if they can shrink that 15 coulomb to 5 coulomb, that will be like, shut up, take money. So this is what they are trying to do. And again, you cannot bypass hardware latency. Hardware latency has to be reduced in hardware itself. And again, at these sort of stupid frequencies, this sort of stupid speed, every centimeter is a latency. So more switches, basically, it will allow your network to work much quicker. It's like the time period, even this house has that time period was like, I'm transmitting, I'm waiting. If you shrink all of that, it's like, whew. And again, that's why you can see that shoreline issue. The SoC is in the center and all the optical fiber is on the back. Now they have shrunk it, put it in the layer and had direct connection in Z axis. That's why NVIDIA does not have this alternative. And again, this technology can push and solve the core bottleneck as of now. So I can easily see if this works out, slow change, and then randomly a massive change was like, whoa, AI is actually able to be your girlfriend. It's like, whoa. And again, you never want one company to do everything. You do not want NVIDIA only. You want other companies to be there. And I really hope some other company really look into the potential and again, test it. Do they actually have the ability to deliver? If they do, dump money into it like there is no tomorrow. Because again, they can scale much quicker. Like they can even give AMD a chance. They can like, hey, Intel, make your GPUs. I can make them fly. That's how big of a jump we are talking about. Assuming they have the software framework. So it's an amazing future. We want this. We need this. So this was my presentation on basically Lightmatter Superchip. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.